Our universe runs on two rulebooks that cannot both be true. One governs the impossibly small, where particles pop in and out of existence. The other describes the cosmic dance of planets and black holes. These two pillars of physics, quantum mechanics and general relativity, are in a silent war, and their battle threatens to unravel our understanding of reality itself. By the end of this journey, you will have explored 30 of the most brilliant and bizarre attempts to write a single, universal law. We will see how some theories suggest space is woven from tiny loops, while others claim our entire cosmos is a holographic projection. What would it mean if gravity was not a fundamental force, but an illusion born from chaos? The quest to unite these worlds is the greatest puzzle in all of science. Which idea feels like it could be the key to everything? The first contender in this grand unification war is called loop quantum gravity. It begins with a radical, almost tactile idea. Forget the smooth, continuous fabric of spacetime you see in diagrams. Loop quantum gravity proposes that space itself is woven together from the tiniest possible threads, one-dimensional loops so small they have no thickness at all. These fundamental loops link and knot together, forming a dynamic, ever-changing network. This is the quantum fabric of reality, a literal weave where each intersecting loop creates a tiny grain of space, a pixel in the cosmos. The theory does not just place particles in space, it makes space itself from something more fundamental. This process is called quantizing geometry, meaning space and time come in indivisible, discrete units. There is a smallest possible volume, a smallest possible area. You cannot have half a quantum of space, just as you cannot have half an electron. Our smooth, vast universe emerges from this frenetic, granular quantum weave when you zoom out, much like a digital photograph looks smooth from a distance but reveals its pixels when examined closely. One of the most profound consequences of this granularity is what it does to the beginning of everything. In Einstein's general relativity, the Big Bang is a singularity, a point of infinite density where the laws of physics break down. But in the granular world of loop quantum gravity, you cannot compress matter and energy into an infinitely small point because there is no such thing. There is a smallest possible size, so as you rewind the cosmic film, the universe reaches this minimum scale and then, according to the mathematics, rebounds. The collapse of a previous cosmos becomes the birth of our own. This is the Big Bounce, a cyclical universe without a true beginning or end, forever breathing in and out. Another victory for the theory is how it handles gravity. It is what physicists call background independent. This means the loops and their relationships define space and time. They do not exist within a pre-existing stage. The stage is built by the actors as they perform. This elegantly incorporates the core insight of general relativity, that gravity is the shape of spacetime itself. Yet for all its beauty, loop quantum gravity faces a monumental challenge. While it brilliantly quantizes the geometry of space, weaving the stage itself from quantum threads, it has struggled to convincingly populate that stage. Incorporating the other fundamental forces and the particles of matter, and then showing how this quantum weave smoothly stitches itself back into the familiar, continuous spacetime of Einstein's equations on large scales, remains an unfinished symphony. It is a breathtaking vision of a granular cosmos, but one still searching for its complete cast of characters. While one theory weaves space from loops, another reimagines the very ingredients of reality. String theory is perhaps the most famous and ambitious contender in the quest for quantum gravity. It proposes a universe built not from point-like particles, but from unimaginably tiny, vibrating strings. Each distinct vibration pattern of a string corresponds to a different fundamental particle. One note might be an electron, another a quark, and a specific closed-loop vibration would be the carrier of gravity itself, a particle called the graviton. In this elegant vision, all forces and matter are unified as different melodies played on the same cosmic instrument. For the mathematics of these vibrations to work harmoniously, however, the strings cannot live in our familiar 3 dimensions of space and 1 of time. They require a grander stage. String theory demands extra dimensions, curled up and hidden at every point in space, too small for us to perceive. Some versions of the theory need 10 total dimensions, others 11. This leads to the idea of a cosmic landscape, a vast, perhaps infinite, collection of possible universe configurations with different physical laws. Our universe, with its specific constants and forces, would be just one fertile valley in this sprawling, multidimensional terrain. Over decades, physicists developed several distinct versions of string theory, named Type 1, Type 2a, Type 2b, and heterotic. For a time, these appeared to be competing theories. Then came a revelation often called the second superstring revolution. A deeper framework known as M-theory emerged, suggesting these 5 string theories were not rivals, but different faces of a single, more fundamental 11-dimensional reality. They were like different maps of the same unknown continent. The mathematical beauty and unifying power of string theory are undeniable, offering a potential theory of everything. Yet, this grandeur comes with a profound cost. The energy scales required to see strings or probe the extra dimensions are far beyond anything our particle colliders can ever reach. This leads to its most persistent criticism that it may be untestable. Without a unique, definitive prediction that can be checked by experiment, some argue it resides in the realm of philosophy rather than empirical science. It is a symphony of stunning mathematical elegance, playing in dimensions we cannot see, for an audience we are not sure can ever truly listen. Amidst the grand symphonies of strings and loops, a quieter, more methodical approach is building reality from the ground up. Causal dynamical triangulations takes a profoundly different path. Instead of vibrating strings or woven loops, it constructs spacetime from the simplest possible geometric shapes, tiny triangular blocks called simplices. Think of it as the ultimate cosmic Lego set where the fundamental bricks are 4-dimensional pyramids. The theory's genius lies in its rules for assembly. Each block must connect to others in a way that strictly respects cause and effect. A cause must always come before its effect, creating a clear, step-by-step evolution. This causal rule is the guiding principle, preventing the quantum foam from becoming a chaotic, timeless mess. Researchers then set these digital blocks in motion using powerful computer simulations, specifically Monte Carlo methods. This technique allows them to randomly sample quadrillions of possible configurations, letting the laws of physics themselves select the most probable shapes of spacetime. The result is nothing short of magic. You start the simulation with a random, frothing jumble of these geometric blocks, a quantum soup with no discernible order. Yet, as the program runs, following the simple causal rules, something remarkable happens. From the utter chaos, a smooth, 4-dimensional universe spontaneously crystallizes. It is as if you shook a box of miscellaneous Lego pieces for long enough, and they suddenly snapped together into a perfect, expansive castle. The simulation does not assume large-scale smoothness, it derives it. This emergence of our familiar, continuous spacetime from a disordered quantum beginning is the theory's greatest triumph. It demonstrates that the 4-dimensional world we experience could be a statistical average, a stable phase that naturally arises from deeper, chunkier rules. Causal dynamical triangulations offers a tangible, computable glimpse into the birth of geometry itself, proving that sometimes to see the universe clearly, you must first break it into a billion tiny pieces. But what if gravity is not broken, just misunderstood? The fourth approach, asymptotic safety in quantum gravity, offers a radical fix. It begins with a problem so deep it threatened to derail the entire field. When physicists try to apply the standard quantum toolkit to gravity, the math explodes. Calculations yield infinite, nonsensical answers, a flaw known as non-renormalizability. It seemed gravity refused to be tamed by the rules that worked for every other force. Asymptotic safety proposes a brilliant escape route using a tool called the renormalization group flow. Think of this as a cosmic zoom lens. As you zoom into higher and higher energies, the effective strength of forces can change. For electromagnetism, the charge you feel gets stronger as you look closer. The theory suggests gravity behaves differently. It predicts the existence of a special anchor point in this mathematical landscape, a non-Gaussian fixed point. At this unique spot, the flow of gravity's strength comes to a halt. If the theory's parameters are precisely tuned to start at this point, then no matter how far you zoom in to the most extreme energies, the theory remains well-behaved and predictable. The infinities are avoided not by adding new dimensions or objects, but by gravity's own inherent quantum nature. A stunning consequence of this fixed point is that gravity may actually become weaker, not stronger, at the highest energies near the Big Bang. This could prevent the singularity, offering a natural resolution to how the universe began. Crucially, asymptotic safety works within the familiar 4 dimensions of space-time and is designed to seamlessly incorporate the known particles and forces of the standard model. It aims to be a complete extension of our current physics, not a wholesale replacement, and because it makes definite calculations, it promises testable predictions. It could alter the evaporation of black holes, leaving a faint signature in cosmic rays, or imprint unique patterns on the oldest light in the universe, the cosmic microwave background. This is a theory betting that the key to quantum gravity has been hidden in plain sight all along, waiting within the complex flow of gravity itself. The fabric of reality may be built from a ledger of pure events. Causal set theory offers perhaps the most minimalist vision of them all. It proposes that space-time, at its most fundamental level, is not a smooth continuum or a geometric weave, but a vast collection of discrete, indivisible events. Think of these as the atoms of space-time itself. They have no shape, no size, no dimensionality in the traditional sense. What defines them is their relationships to one another. Each event is connected to others by a single, primitive link causality. One event either precedes another or it does not. This creates a vast, shimmering network of before and after connections, a cosmic family tree of cause and effect. From this astonishingly sparse starting point, everything else must emerge. The theory's core mantra is order plus number equals geometry. The order is the web of causal connections. The number is simply how many of these atomic events exist in a given region of the network. The theory proposes that from these 2 simple ingredients, the full 4-dimensional geometry of spacetime, with its distances and its curvature, can be mathematically reconstructed. Our smooth universe of planets and stars is a blurry, large-scale approximation of this underlying pointillistic reality. This framework naturally embraces one of the most profound ideas in modern physics, the holographic principle. The information needed to describe a volume of space may be encoded on its bounding surface. In a causal set, the number of elements in a region is finite, directly giving a limit to how much information that region can contain. It builds a cosmic speed limit and a maximum density right into the foundation of reality. This also provides an elegant escape from the nightmare of singularities. In the heart of a black hole or at the Big Bang, where general relativity predicts infinities, the causal set simply runs out of elements. There is no infinite density because there is no continuum to become infinitely dense, just a finite number of events. The appeal of causal set theory is deeply philosophical. It elevates causality from a consequence of spacetime to its very creator. Before there is space or time, there is cause and effect. The universe, in this view, is not a place where things happen. it is the happening itself, frozen into an eternal, crystalline structure of relationships. It is a universe written not in geometry, but in pure story. The story of space-time may be written in a language where words refuse to sit still. Non-commutative geometry proposes a universe where the very coordinates of reality, the labels for position and time, are not simple numbers. They are mathematical objects that do not commute. This means that measuring position in one direction and then another does not necessarily give the same result as measuring them in the opposite order. This is a familiar feature in the quantum world, where you cannot precisely know both a particle's position and its momentum at the same time. But here, this fundamental uncertainty is applied to the stage itself. If the coordinates of spacetime do not commute, then the concept of a sharp, pinpoint location loses all meaning at the tiniest scales. Space becomes inherently fuzzy, like a photograph blurred by its own quantum grain. This fuzziness imposes a natural limit, a smallest possible resolution for the universe, effectively quantizing geometry in a deeply algebraic way. The mathematical architecture for this vision was largely built by the mathematician Alain Connes. His framework is not about adding new particles or dimensions, but about redefining the very geometry upon which physics is built. In this view, the smooth, continuous space of our daily experience is an approximation, a classical shadow of a far more complex, non-commutative quantum reality. One of the most compelling applications of this new geometry is its potential to unify forces. Remarkably, Connes' framework can naturally incorporate the entire standard model of particle physics, deriving its forces and particles from the geometric properties of this non-commutative space. Gravity in this picture is not an added force, but emerges from the metric, the distance measuring rules of this fuzzy geometry, just as it does from the curvature of spacetime in Einstein's theory. This offers a profound possibility that all fundamental interactions, from the nuclear forces to gravity itself, share a common geometric origin. This inherent fuzziness also provides elegant solutions to the most vexing infinities. In the heart of a black hole, where classical geometry predicts a singularity of infinite density, the non-commutative fuzziness would smear out the point of collapse. There is no infinitely sharp pinprick because the universe has no such thing as an infinitely sharp point. The singularity is replaced by a dense but finite region of extreme curvature, a quantum foam where the very notion of here and there dissolves into a probabilistic cloud. It is a theory that suggests the ultimate laws of reality are written not in the language of shapes, but in the algebra of relationships, a cosmic code where uncertainty is not a bug, but the foundational feature of existence. Gravity might be the most familiar illusion in the cosmos. This seventh theory proposes a truly radical shift, that gravity is not a fundamental force of nature at all. It is an emergent phenomenon, a side effect of something more primal, much like temperature is not a fundamental property but emerges from the frantic motion of countless molecules. This idea, championed by physicist Eric Verland, suggests gravity is a consequence of information and entropy. Entropy is a measure of disorder, and in thermodynamics, systems naturally evolve toward higher entropy. Verland's entropic gravity applies this principle to spacetime itself. He imagines that what we perceive as empty space is actually filled with fundamental degrees of freedom, like microscopic storage units for information. When a massive object like a star is placed in this space, it disturbs the arrangement of this information. The entropy or disorder in the surrounding region changes. According to Verland, gravity is simply the force that arises as nature seeks to maximize this entropy. An apple falls to the ground because that is the direction in which the total entropy of the system, including the apple, the earth, and the fundamental information bits of space, increases. It is a staggering reconceptualization where attraction is not a pull but a statistical tendency. From this single, elegant starting point, Verland showed he could derive Newton's famous law of universal gravitation, not by assuming a force, but by calculating entropic change. Even more provocatively, his framework offers a new perspective on one of cosmology's greatest mysteries, dark matter. In the standard view, dark matter is an invisible, mysterious substance whose gravity holds galaxies together. In entropic gravity, the need for this extra substance vanishes. The observed rotational speeds of stars around galaxies, which famously defy Newton's predictions, could instead be explained by the entropy gradient associated with the visible matter alone. The extra gravitational effect we attribute to dark matter might simply be how gravity behaves on galactic scales when understood as an entropic force. This has sparked intense debate within the physics community. Proponents see it as a profound unification, weaving together thermodynamics, information theory, and gravity into a single tapestry. Critics argue the theory is not yet fully developed, lacking the precise, testable predictions that could distinguish it from the dark matter paradigm. The central question it forces us to confront is deeply philosophical. Is gravity a real, fundamental interaction woven into the fabric of reality, or is it merely a compelling illusion, a shadow cast by the deeper, invisible dance of information and disorder? The universe may be a magnificent illusion, a cosmic sleight of hand. This is the startling claim of the holographic principle. It states that all the information contained within any volume of space can be perfectly described without any loss by physics operating only on that volume's two-dimensional boundary. Think of a three-dimensional sculpture, and then imagine that every single detail about that sculpture is encoded on its two-dimensional surface, like a fantastically complex barcode. The interior in this radical view is not truly separate. It is a projection, a hologram generated from the data on the edge. The origins of this idea are as counterintuitive as the idea itself, born from the fiery paradoxes of black holes. When matter falls into a black hole, it seems to vanish, taking all its information with it. But Stephen Hawking showed that black holes also radiate energy and slowly evaporate. This created a crisis. If the black hole eventually disappears, what happens to all that information? Does it vanish forever, violating a sacred principle of quantum mechanics? Physicists Gerard T. Hooft and later Leonard Susskind proposed a revolutionary answer. They argued that the information of everything swallowed by the black hole is not lost inside, but is instead smeared and preserved on the black hole's event horizon, its point of no return. The three-dimensional interior is an emergent description, while the true information-theoretic reality is painted on the two-dimensional surface. This insight was transformed from a clever idea about black holes into a precise mathematical framework through a discovery called the anti-de Sitter space conformal field theory correspondence, often shortened to ADS/CFT. It is the holographic principle in its most powerful and testable form. The correspondence proposes a perfect dictionary-like duality between two completely different kinds of worlds. On one side of this dictionary, you have a universe with gravity, described by string theory, living in a special curved space called anti-de Sitter space. On the other side, you have a quantum field theory, a system very much like our own standard model of particles, but one that lives only on the flat, lower dimensional boundary of that curved space. Astonishingly, every single event, every particle interaction, every gravitational warping in the bulk of the curved space has a perfect, one-to-one translation into the language of particles and forces on the boundary. It means a calculation that is impossibly difficult in the gravity world can become a much simpler calculation in the particle world, and vice versa. The implications for quantum gravity are staggering. It suggests that gravity itself and the three-dimensional space we inhabit may not be fundamental. They could be collective, emergent phenomena that arise from the complex quantum interactions of countless fundamental degrees of freedom living on a distant two-dimensional surface. Our rich three-dimensional reality, with its galaxies, planets, and people, might be a grand projection, a holographic movie playing out on the cosmic film of a lower dimensional screen. This forces a humbling question: are we living inside the universe, or are we merely a shadow on its wall? The holographic screen is not the only place where reality is rewritten. Deep within the framework of loop quantum gravity lies a dynamic counterpart to its static weave. If the spin network is a single, frozen snapshot of quantum space, then its history, its evolution through time, is described by a spin foam. Picture a spin network, that web of linked loops defining space at one instant. Now let it breathe. As it evolves, the connections between nodes change, links are created and annihilated. If you stack all these successive snapshots on top of each other, you get a complex three-dimensional structure that looks remarkably like a froth of soap bubbles, a delicate lattice of intersecting surfaces. This is the spin foam, and it represents the entire history of quantum spacetime, a four-dimensional process captured in a single, intricate object. The foam is more than just a pretty picture. It is a precise mathematical tool for calculating how the universe transitions from one quantum geometry to another. This approach is known as a sum over histories, or a path integral for gravity. In ordinary quantum mechanics, to find the probability that a particle goes from point A to point B, you must consider every single possible path it could take, even the wild, looping ones, and sum their contributions. Spin foam models apply this profound idea to the fabric of reality itself. To find the probability that the universe evolves from one spin network state to another, you must sum over all possible spin foams, all possible histories of quantum spacetime bubbles that connect the two. Our classical, smooth universe emerges as the most probable, coherent history in this vast quantum ensemble. Each bubble in the foam, each tiny cell, represents a fundamental quantum of spacetime. Their interactions, their mergers and splits, are the elementary events from which the flow of time itself is built. This makes spin foams a powerful tool for probing the most extreme environments, like the origin of the cosmos or the heart of a black hole where classical geometry shatters. One of the theory's most significant successes has been in calculating black hole entropy. Using spin foam techniques, physicists can count the number of microscopic quantum states that correspond to a black hole of a given size. The result they derive matches the famous formula Stephen Hawking discovered from thermodynamic arguments, where a black hole's entropy is proportional to the area of its event horizon. This provides a deep explanation for why black holes have entropy at all. It is the logarithm of the number of ways the quantum geometry at the horizon can be arranged. Spin foam models are the dynamic, breathing story of the universe written in the language of quantum geometry, a story where every possible history bubbles up from the quantum vacuum, and our reality is the tale that tells itself most often. Sometimes the most elegant solution is to break a sacred rule. This 10th theory, Lifshitz gravity, dares to do exactly that. For over a century, a principle called Lorentz invariance has been a cornerstone of modern physics. It states that the laws of physics, and crucially the speed of light, are the same for all observers, no matter how fast they are moving. This symmetry between space and time is woven into the heart of Einstein's relativity. But physicist Petr Horava asked a heretical question: what if this perfect symmetry is only an approximation, a low-energy illusion? His radical proposal is to treat time and space differently at the most fundamental, high-energy levels. This is called anisotropic scaling. In this view, time is not just another dimension, it holds a privileged, distinct role. Think of it like watching a high-definition video. At normal speed, the motion appears smooth and continuous. The dimensions of space and time seem perfectly symmetric. But if you could slow the film down to examine each individual frame, you would see the truth that time progresses in discrete steps separate from the spatial pixels on the screen. Holography's gravity applies this logic to the fabric of reality itself. By breaking the deep symmetry between space and time at ultra-high energies, the mathematics of quantum gravity suddenly become manageable. The infinities that plague other approaches, the non-renormalizability, simply vanish. The theory becomes well-behaved and calculable. This modification of Einstein's equations in the ultraviolet, the high-energy realm, has a profound consequence for the beginning of everything. It can naturally resolve the Big Bang singularity without the strict union of space and time enforced by Lorentz invariance. The equations suggest the universe could have emerged from a non-singular bounce or a phase transition rather than an infinitely dense point. The early universe in this picture was a place where time behaved differently, allowing for a graceful birth. One of the most exciting and testable predictions of Holographic gravity involves the speed of light itself. In this framework, the speed of light is not a constant across all energies. At the tremendous energies of the early universe, light may have traveled faster or slower than it does today. This energy-dependent speed of light could leave an imprint on the oldest light we can see, the cosmic microwave background. Subtle patterns in this fossil radiation might one day reveal whether light in the infant cosmos broke the universal speed limit we observe today. It is a theory born from a deliberate act of rebellion, suggesting that to heal the rift between quantum mechanics and gravity, we must first allow time to step out of the shadows and reclaim its own unique rhythm. The universe may have been born from a boiling sea of disconnected whispers. Group field theory pushes the quantum geometry of loops and foams into a startling new phase. It asks, if spin networks are the atoms of space, what is the quantum field from which these atoms condense? The answer is a theory where the fundamental field is not defined over points in space, but over abstract mathematical spaces called group manifolds. Each excitation of this peculiar field represents a single quantum of geometry, a tiny chunk of potential space. In this vision, the basic building blocks of reality are not yet arranged into any coherent structure. They exist in a primordial, pre-geometric soup. The theory's true power lies in its organizing principle. Group field theory is a second quantized framework. This means it does not just describe individual quanta of space. It describes the processes by which these quanta are created, annihilated, and interact. Much like a quantum field theory for particles describes how electrons and photons come and go. The history of these interactions is mapped out by Feynman diagrams, the same tool used to calculate particle collisions. But here, the diagrams are not lines of particles. They are the intricate, bubbly structures of spin foams. In a beautiful synthesis, the spin networks of loop quantum gravity and their dynamic histories, the spin foams, emerge naturally as the Feynman diagrams of group field theory. They are not assumed, they are calculated, the most probable pathways for geometry to assemble itself. This allows the theory to tackle the ultimate question: how did something come from nothing? The pre-geometric phase is a state of no classical spacetime, a boiling vacuum where quanta of geometry flicker in and out of existence, disconnected and chaotic. Then, through a process akin to condensation, like water vapor cooling into droplets, these quanta begin to interact and bond. Their random connections become coherent, and from the formless noise, a stable, large-scale spin network crystallizes. This network is our universe's first instant of space. Group field theory aims to describe this phase transition, the moment geometry itself was born from a state of pure quantum potential. It is a theory of cosmic genesis written in the language of quantum fields, suggesting that before there was a universe, there was only a silent, seething probability of one. Gravity may carry a hidden twist in its geometric fabric. Our 12th theory, quantum Einstein-Cartan theory, proposes that the stage of spacetime is not merely curved, it is also subtly twisted. In Einstein's original vision of general relativity, gravity is the curvature of space-time, a bending caused by mass and energy. But what about the intrinsic spin of particles, like the constant rotation of an electron? The mathematician Eli Cartan argued that spin should leave its own geometric imprint, a property called torsion. Think of curvature as bending a flexible sheet, while torsion is like twisting it. In this richer geometry, the connection, the mathematical rule that tells vectors how to move from point to point, is no longer symmetric. It contains this twist directly sourced by the quantum spin of matter. This means every electron, every quark, every fundamental particle with spin is not just a passenger on the geometric stage. It is a tiny architect imparting a microscopic twist to the very fabric it moves through. This twist has a profound consequence for the darkest pits of gravity. In classical general relativity, when a massive star collapses, matter is crushed into an infinitely dense point, a singularity. But when torsion is included in the equations, something remarkable happens. As matter is compressed to extreme densities, the spin of particles becomes aligned, and the collective torsion they generate produces a repulsive force. This force grows stronger as the collapse continues, eventually halting it and causing a rebound. The big crunch becomes a big bounce, a cosmic rebirth without a singular beginning. This offers a compelling, geometric alternative to the mysterious dark energy or exotic matter often invoked to explain a cyclical universe. Furthermore, quantum Einstein-Cartan theory finds a natural and elegant home within the framework of loop quantum gravity. While loop quantum gravity provides a beautiful quantum description of curved space, it traditionally struggles to fully incorporate matter. The Cartan twist, with its direct link to particle spin, offers the perfect bridge. It allows the quantized loops of space to couple directly to the fermions, the spin one-half particles that make up our material world. In this synthesis, the spin of a particle and the spin of a quantum loop of space are not separate concepts, but deeply intertwined aspects of a single geometric reality. The universe, in this view, is a dynamic dance where matter tells geometry how to twist, and twisted geometry tells matter how to move, all woven together at the quantum level. Roger Penrose saw the stage of space-time and decided to build it from light. His twistor theory begins with a profound reversal. Instead of starting with points in space and time, it proposes that points are secondary, derived from more fundamental geometric objects called twistors. A twistor is not a particle or a string, but a mathematical entity that naturally encodes both a point in space-time and the momentum and spin of a massless particle moving through that point. In essence, a twistor represents a ray of light, a complete history of a photon, frozen into a single, elegant object. This makes twistor space the perfect language for describing the world of massless particles like photons and gluons and their interactions. The complex, messy calculations of how such particles scatter off one another, which in standard quantum field theory involve pages of intricate algebra, often become astonishingly simple and geometric in twistor space. Lines and curves in this abstract space correspond directly to particle trajectories and interactions, revealing hidden patterns and symmetries. This success in calculating scattering amplitudes in gauge theories, the frameworks describing forces like electromagnetism and the strong nuclear force, was a major victory. It showed that twistor theory was not just beautiful mathematics, it was a powerful computational tool that could crack problems deemed intractable by other means. But Penrose's ambition was far grander. His ongoing program seeks to use twistors to reformulate the very geometry of spacetime from the ground up. The goal is a complete twistor description of quantum gravity, where not just massless particles, but the fabric of gravity itself emerges from the relationships between these fundamental objects. In this vision, our familiar four-dimensional universe of events and intervals is a shadow, a derived concept. The The true pre-geometric reality is the twistor space, a realm where locality and perhaps even time as we know it do not exist in their current form. The dream is to see Einstein's equations for gravity crystallize out of the holomorphic or complex analytic geometry of twistor space. It is a theory that asks us to believe that the universe is not built from stuff in a place, but from relationships between threads of light, and that if we could only read this luminous code, the quantum nature of gravity would shine through with undeniable clarity. Space itself could be the only actor in the cosmic play. Shape dynamics offers a radical reinterpretation of Einstein's masterpiece, suggesting that what we perceive as spacetime is really just the evolving shape of pure space. This theory proposes a perfect, yet startlingly different, dual description of general relativity. In the standard view, spacetime is a unified four-dimensional block, where the division between past, present, and future is relative. Shape dynamics dismantles this block. It discards spacetime as a fundamental entity and replaces it with a sequence of three-dimensional spatial geometries, each with a fixed, universal notion of time. The theory's central principle is spatial conformal invariance. This means that the physics does not care about the absolute size of the universe at any given moment, only its shape, the angles between points, the curves, and the proportions. Imagine a balloon being inflated. The rubber stretches, changing the distances between every marked point. In shape dynamics, that overall scaling is physically meaningless. Only the pattern of the marks, the relational arrangement, carries true physical information. To achieve this, the theory makes a profound trade. It surrenders Einstein's relativity of simultaneity, the idea that observers moving at different speeds will disagree on which events are now, and in return, it gains a single global clock that ticks for everyone. This addresses one of the most vexing issues in quantizing gravity, the notorious problem of time. In standard quantum gravity approaches, time often vanishes from the equations, leaving a frozen, static picture of the universe. By restoring a fixed temporal order from the start, shape dynamics provides a cleaner, more direct route to a quantum theory of the shape of space. Remarkably, this is not a rival to general relativity, it is its perfect twin. Every solution in Einstein's theory has a corresponding solution in shape dynamics, and they predict identical outcomes for all physical observations. They are two languages describing the same reality. Yet, by speaking the language of shapes rather than spacetime, new vistas open up, particularly for the quantum birth of the cosmos. Quantum cosmological models built on this foundation can focus purely on the probability of the universe having a certain shape, evolving through a sequence of shapes without wrestling with the nebulous concept of a beginning in time. It suggests the universe's first moment was not a point in spacetime, but the first shape in a succession, emerging from a timeless quantum fog where only pure geometry fluctuated. Gravity might be the only force in nature that feels weightless. For decades, physicists have assumed its hypothetical carrier particle, the graviton, is massless, just like the photon. This assumption is woven into the very fabric of general relativity, dictating that gravity's influence stretches to infinity, bending starlight and holding galaxies together across the void. But what if this is wrong? The 15th theory, massive gravity, dares to challenge this cornerstone. It proposes that gravitons possess an incredibly tiny but non-zero mass. This seemingly minor tweak would fundamentally alter how gravity works over vast cosmic distances, potentially solving mysteries that have puzzled astronomers for a generation. The idea, however, was long considered a ghost story. Early attempts to give gravity a mass introduced catastrophic instabilities into the equations, phantom excitations called Boulware-Desir ghosts that rendered the theories nonsensical. There was also the V-Divisy discontinuity, a mathematical cliff showing that even an infinitesimally small graviton mass would produce predictions wildly different from Einstein's theory. contradicting precise solar system tests, we know his equations pass with flying colors. For over 40 years, these problems seemed insurmountable, consigning massive gravity to the theoretical graveyard. Then, a resurrection. In 2010, physicists Claudia de Ram, Gregory Gabadats, and Andrew Tolley achieved a breakthrough. Their DRGT model, named with their initials, constructed a theory of massive gravity that was ghost-free. They built it like a master locksmith, adding specific, finely tuned interaction terms that cancelled out the deadly instabilities at every level. The theory now had a solid mathematical foundation. A massive graviton would change gravity's character in profound ways. Unlike the infinite reach of a massless force, a massive gravity would have a finite range, decaying exponentially beyond a certain cosmic scale. This could manifest in the ripples of spacetime themselves. Gravitational waves from colliding black holes might travel at a speed slightly different from light if the graviton has mass, a subtle fingerprint future observatories like LISA may one day detect. More dramatically, this could reshape our understanding of the cosmos's expansion. The mysterious dark energy accelerating the universe might not be a new form of energy at all, but a sign that gravity itself is weakening over the largest distances. In this view, the accelerated expansion is not a push from dark energy, but a pull that fades, as if gravity grows tired across the cosmic expanse. This would effectively make gravity a fifth force with a very long but finite reach. The implications are staggering, suggesting that the force which sculpts planets also forgets how to bind the universe together on the grandest stages. It is a theory that asks if the most familiar pull in our lives is, in fact, hiding a secret weight of its own, a mass so small it has taken the lifespan of the universe to reveal its absence. Perhaps gravity's equations need a rewrite, not an addition. While many theories seek to quantize gravity, others ask a simpler, more radical question. What if Einstein's theory, while brilliant, is incomplete on cosmic scales? This 16th idea, modified gravity, proposes that the geometric rules themselves must change. The most famous of these alternatives is f of r gravity. In Einstein's general relativity, the left side of his famous equation is built from the Ricci scalar, a single number r that measures the average curvature of spacetime. This term acts like a spring's tension, dictating how spacetime responds to matter and energy. F of r gravity replaces this simple r with a more complex function, f of r. This is not a minor tweak. It is like replacing a simple spring with an intelligent, adaptive material that stiffens or softens depending on how much it is stretched. The consequences of this change are profound, especially for the fate of the cosmos. One of the great triumphs of f of r gravity is its ability to explain the accelerating expansion of the universe without invoking the mysterious dark energy. In this framework, the function f of r is crafted so that in the low-density, vast emptiness of intergalactic space, the geometry of the universe naturally produces a repulsive effect. The vacuum itself, through its modified curvature, pushes galaxies apart. The acceleration is not driven by an unknown energy permeating space, but by space's own altered response to being nearly empty. This is a compelling shift in perspective, turning a substance problem into a geometric one. F of r is not the only player in this modified game. Other theories introduce even more intricate geometric terms. Gauss-Bonnet gravity, for instance, incorporates a specific combination of curvature squares that becomes significant only in very high-dimensional spaces or extreme environments, offering another path to dark energy and singularity resolution. Yet, the path for these theories is a razor's edge. They must perform a delicate balancing act, explaining the bizarre behavior of the universe on the largest scales while simultaneously passing the exquisitely precise tests we have right here in our own solar system. Einstein's theory predicts the exact amount by which Mercury's orbit precesses, the precise bending of starlight by the sun, and the timing of signals from orbiting satellites. Any modification that alters gravity to explain cosmic acceleration risks breaking these well-verified local laws. The theories must include a screening mechanism, a mathematical cloak that makes the modified gravity effects hide in regions of high density, like our solar system, but unleash them in the void between galaxies. This is the core challenge, walking the fine line between being a true alternative to dark matter and dark energy, and simply becoming an overly complicated description of the same phenomena. Are we witnessing the influence of invisible substances, or are we finally reading the fine print in gravity's contract with the cosmos? A black hole's horizon is the ultimate cosmic trapdoor, a point of no return where gravity's grip becomes absolute. Yet, this serene boundary may hide a hidden inferno, a paradox so fierce it threatens to incinerate our most cherished principles. This is the firewall problem, a thought experiment that sets three pillars of physics on a collision course. First, quantum unitarity demands that information can never be truly destroyed. It must be preserved even if scrambled beyond recognition. Second, Einstein's equivalence principle assures an astronaut crossing the event horizon would feel nothing special, experiencing free fall in empty space. Third, the principle of locality states that physical effects are caused by nearby interactions, not by mysterious actions at a distance. The AMPS paradox, named for its creators Olmary, Marolf, Pulczynski, and Sully, shows you cannot keep all three. If information escapes a black hole via subtle Hawking radiation, as unitarity requires, then that radiation must be entangled with particles just inside the horizon. But for the radiation to also be pure and carry the information out, those interior particles cannot also be entangled with their partners farther inside. This is a quantum monogamy violation, an impossibility. The brutal resolution proposed is that the entanglement must be violently broken right at the horizon. This severance would release a wall of unimaginable energy, a firewall that would incinerate any astronaut long before they crossed into the black hole's depths. The serene horizon becomes a lethal boundary, violating the equivalence principle in the most dramatic way possible. This paradox is not a flaw in nature, but a glaring spotlight on the incompatibility of our current theories when pushed to extremes. It forces physicists to choose which sacred principle to sacrifice. Some, like Leonard Susskind, advocate for black hole complementarity, suggesting the infalling observer and the distant witness see two different, mutually exclusive realities that are both correct in their own frames. Others propose the final state projection model, where quantum mechanics is modified so that at the singularity, a final boundary condition projects the information back out, resolving the conflict. The firewall screams that our understanding of spacetime is fundamentally incomplete where gravity and quantum mechanics meet. It tells us that the smooth, classical geometry of Einstein must give way to something far stranger, a quantum structure where locality or equivalence might be approximate illusions. The event horizon is not just a line in space, but a frontier where the very meaning of reality is being decided. The firewall is a paradox screaming for a bridge, and two giants of physics may have built one from the fabric of entanglement itself. The ER equals EPR conjecture, proposed by Juan Maldacena and Leonard Susskind, is a deceptively simple equation with universe-altering implications. It states that an Einstein-Rosen bridge, the theoretical wormhole connecting two distant points in spacetime, is the same thing, is physically equivalent to the quantum entanglement between two particles, famously described in the EPR paradox by Einstein, Podolsky, and Rosen. This is not just an analogy. It proposes that the spooky action at a distance that so troubled Einstein has a geometric shape, a microscopic, non-traversable tunnel in the fabric of reality. Imagine two entangled electrons, one here on Earth, another on a planet orbiting a star 1,000 light-years away. Measure one, and the other instantly assumes a correlated state. According to this conjecture, linking them is not an invisible force, but a physical structure, a wormhole so incredibly tiny and dynamic it defies our classical notions of a tunnel. This wormhole is not for travel, it is a geometric manifestation of their quantum connection. The power of this idea shines a brilliant light directly on the firewall paradox. Recall the problem: to preserve information, the Hawking radiation must be entangled with particles both inside and outside the black hole, a quantum impossibility. ER equals EPR offers an escape. It suggests the entanglement between the escaping radiation and the black hole interior is not a problem to be solved, but a bridge to be recognized. That entanglement is the wormhole. The interior of the black hole and the distant radiation are not separate entities connected by mysterious signals. They are geometrically linked. The information never had to cross the forbidden horizon. It was always connected via this microscopic bridge. The terrifying firewall, in this view, may simply not exist because the horizon is not a place where entanglement is severed, but where it is woven into the geometry of spacetime itself. This leads to the conjecture's most profound implication, a new vision for the origin of spacetime. If every quantum entanglement creates a tiny wormhole thread, then the vast, connected fabric of our universe could be an immense web of these threads woven together. Spacetime does not give rise to entanglement. Entanglement gives rise to spacetime. This is the heart of it from qubit philosophy, whether it is the classical world of things and distances, and the qubit is the fundamental unit of quantum information. Our experience of being here, separated from there, may be an illusion born from a cosmic tapestry of quantum connections. The universe is not a container where things happen. It is the happening itself, a dynamic network of relationships made real. Space may have begun as a perfect, silent conversation between everything and everything else. Quantum gravity proposes that in its earliest, hottest state, the universe was not a place but a complete graph. Picture a vast network where every single fundamental node, every potential bit of reality, was directly connected to every other node. There were no distances, no dimensions, just total, instantaneous connection. In this seething, high-energy state, the concept of here and there was meaningless because everything was adjacent to everything else. Then, a cosmic freeze. As this primordial network expanded and cooled, the connections began to break. Links between nodes froze out, turning from active, vibrant lines of interaction into inert, disconnected points. This process is not random. It follows an energetic principle where the system seeks its lowest energy state. As more and more links freeze, the once complete graph shatters into a sparse, irregular web. And from this shattering, something miraculous emerges: dimensionality. The pattern of frozen and active connections creates a structure where most nodes are only connected to a few neighbors. This sparse network naturally exhibits the properties of a low-dimensional space, like our familiar 3 dimensions of space plus 1 of time. In this view, dimensionality is not a fundamental property of the universe. It is a phase of matter, an emergent phenomenon that crystallizes as the quantum graph cools. The speed of light itself could be a consequence of this freezing. In the hot, fully connected phase, information could propagate instantly across the entire graph. But as links freeze, information is forced to hop from node to node along the remaining active connections, establishing a maximum speed limit, the cosmic speed of light. This dynamic geometry offers a stunning new perspective on one of cosmology's oldest puzzles, the remarkable uniformity of the cosmic microwave background. Why does the temperature of this ancient light look almost exactly the same in every direction, even between regions that, in a standard expanding universe model, would never have had time to communicate? Quantum gravity suggests an answer. In the initial, fully connected state, every part of the universe was in direct contact with every other part. Thermal equilibrium was established instantly in a single, timeless moment. Then, as the graph froze into our 3+1-dimensional reality, that uniformity was locked in, imprinted on the cosmos like a memory of its former, perfectly connected self. It is a theory where the laws of physics themselves are not written in stone, but are the emergent habits of a network learning to be a universe, one frozen link at a time. The universe's smooth curves might be a mosaic of cosmic tilework. Simplicial quantum gravity, also known as reg calculus, is a theory that builds reality from flat geometric pieces. It discards the idea of a perfectly smooth, curving fabric. Instead, it approximates the complex geometry of spacetime by fitting it together from the simplest possible shapes, higher-dimensional triangles called simplices. A simplex is the generalization of a triangle, a perfectly flat shape in any dimension. A 2-simplex is a triangle, a 3-simplex is a tetrahedron, a 4-simplex is a 4-dimensional pyramid. The revolutionary insight of physicist Tullio Regge was that you could build any curved spacetime geometry you wanted by gluing these flat blocks together along their shared faces. The curvature does not live inside the blocks, which are perfectly flat, but is concentrated at the hinges where they meet, much like the angles between the facets of a cut gem. This method, reg calculus, provides a way to write Einstein's equations of general relativity without ever using a coordinate system. You work purely with the lengths of the edges of these simplices and the angles between them. It is gravity expressed in the language of geometry itself, a discrete, blocky version of Einstein's continuum theory. This discretization is not just a mathematical trick, it is a gateway to the quantum realm. In the path-integral approach to quantum gravity, you must sum over all possible histories of spacetime geometry. In a continuum theory, this is an infinite, impossible sum over every possible smooth shape. But with reg calculus, the space of possibilities becomes manageable. You only need to sum over all the different ways to glue together a finite number of these flat simplices. This turns an abstract quantum calculation into a concrete computational problem, one that can be tackled by powerful supercomputers. Researchers can run simulations that let spacetime foam, exploring the quantum jitter of geometry at the Planck scale by randomly assembling and reconfiguring these simplicial building blocks. In this way, simplicial quantum gravity acts as a vital laboratory for quantum geometry, a testing ground where the statistical behavior of spacetime itself can be probed. Its legacy is profound, serving as the direct mathematical precursor to modern theories like causal dynamical triangulations, which inherits its blocky toolkit but adds the crucial rule of causality to the mix. It reminds us that sometimes, to understand the fluid elegance of the cosmos, you must first learn to build it from scratch, one flat tile at a time. Deep within every particle of matter may lie a secret blueprint for gravity itself. Our 21st theory ventures into the most speculative territory yet, where gravity is not a force of geometry, but a collective behavior emerging from a deeper, more fundamental layer of particle physics. This is the realm of prion models. If quarks and leptons, the electrons, neutrinos, and other building blocks of the Standard Model, are not truly elementary, what are they made of? Prions are the hypothetical answer, the proposed subcomponents of subatomic particles. Imagine them as the ultimate cosmic Lego bricks, combining in different arrangements to build every known particle, much like protons and neutrons are built from quarks. But in some ambitious models, these prions do more than just construct matter. They are also the source of all forces, through their own gauge interactions, a kind of fundamental conversation governed by symmetry. The dance of prions could give rise to the strong nuclear force, the weak force, electromagnetism, and most astonishingly, gravity. In this vision, the graviton, the carrier of gravity, would not be a fundamental entity. It would be a composite particle, a bound state of prions, much like a proton is a bound state of quarks. This offers a breathtakingly simple, particulate origin for everything in the universe, one unified engine generating both the actors and the stage from the same raw material. The appeal is immense, promising a single, elegant framework that bypasses the need to quantize spacetime itself. Instead, gravity emerges naturally from the quantum dynamics of these deeper constituents, potentially solving the unification puzzle in one stroke. Yet the path is fraught with profound challenges. The hierarchy problem screams for attention. Why is gravity so unimaginably weaker than the other forces? If all forces come from the same prion interactions, this wild disparity in strength becomes a mystery that must be engineered into the model with delicate, often unconvincing fine-tuning. More critically, there is a stark lack of any direct experimental evidence. Our most powerful particle colliders have probed to incredibly small scales and have never seen a hint of substructure within electrons or quarks. If prions exist, they must be bound together by a force of unimaginable strength, confining them so tightly that they appear as perfect points at any energy we can access. This makes the theory extraordinarily difficult to test, pushing its predictions far beyond our current technological horizon. It remains a captivating dream of ultimate simplicity, a universe where the pull that shapes galaxies is just the distant echo of the same tiny clicks that build an atom. Time itself may be the universe's most persistent illusion. When physicists attempt to write down a quantum version of Einstein's equations, they encounter a profound and unsettling result: time vanishes. The central equation of canonical quantum gravity, the Wheeler-DeWitt equation, describes the entire cosmos in a single, timeless snapshot. It contains no variable for time at all. This is the frozen formalism problem. In quantum mechanics, time is an external parameter, a stage on which the quantum drama unfolds. But in general relativity, time is part of the dynamic stage itself, interwoven with space. When you try to quantize that stage, the external clock disappears, and the equations describe a static, unchanging quantum state of the entire universe. How can a theory that abolishes time explain a reality where change is the most fundamental experience we have? The conflict is stark. Quantum evolution demands a background time, while general relativity's covariance says there is no preferred time, only spacetime. One proposed solution is to find a material clock within the universe itself. Since no external clock exists, we must use a part of the cosmos to measure the change in other parts. Imagine using the slow, steady ticking of a specific scalar field, a fundamental vibration permeating all of space as a cosmic hour hand. The evolution of other quantum variables, like the size of the universe or the density of matter, is then measured relative to this internal clock. Time becomes relational, defined not by a master clock, but by the correlations between changing things. This leads to a radical philosophical stance. Perhaps time is not fundamental at all. In the timeless perspective, the wave function of the universe does not evolve, it simply is. It encompasses all possible configurations of the cosmos, from the Big Bang to the distant future, in one frozen superposition. Our experience of flowing from one moment to the next is a trick of consciousness, a path we trace through this vast, static landscape of possibilities. We are like readers moving through a book, page by page, while the entire story already exists, complete and unchanging, between its covers. Another approach suggests time emerges from quantum entanglement between subsystems. If you take two parts of a timeless quantum whole and entangle them, the evolution of one can serve as a clock for the other. The flow of time arises from the changing quantum correlations between them, much like the plot of a novel emerges from the relationships between its characters. This means the arrow of time, the reason we remember the past but not the future, could be a consequence of the universe starting in a highly ordered, low entanglement state and progressively becoming more entangled and complex. The problem of time forces us to ask whether our deepest intuition about reality, the relentless forward march of now, is merely a useful story we tell ourselves about a far stranger, timeless quantum reality. Gravity may be the only force with a hidden, dancing partner waiting in the wings. Supergravity emerges from a grander symmetry of the cosmos, one that proposes every fundamental particle has a secret twin. This is supersymmetry, a theoretical framework suggesting that for every known fermion, the matter particles like quarks and electrons, there exists a bosonic superpartner. And for every known boson, the force carriers like photons and gluons, there exists a fermionic twin. This symmetry elegantly solves several deep puzzles in particle physics, stabilizing the mass of the Higgs boson and offering a natural candidate for the universe's mysterious dark matter. But when you weave this symmetry into the fabric of general relativity itself, you get something truly special: supergravity. It is the theory that emerges when supersymmetry becomes a local, space-time transforming principle. The gravitational field gains its own superpartner, a particle called the gravitino. This hypothetical particle is a fermion with a spin of 3 halves, a unique hybrid that carries the quantum of gravitational force while also obeying the statistical rules of matter particles. The gravitino is the dancing partner to the graviton, a direct consequence of the universe's hidden symmetry. One of supergravity's greatest triumphs is its intimate relationship with string theory. In many formulations, supergravity is not a rival, but the effective, low-energy description. It is what string theory looks like when you zoom out from the vibrating strings and see the smooth, classical forces they produce. This makes supergravity a vital bridge, a testing ground where the particle physics of the very small meets the curved geometry of the very large. Its mathematical structure is breathtakingly elegant, often described by physicists as too beautiful to be wrong, with equations that possess a natural harmony and simplicity. Yet, for all its beauty, supergravity faces a formidable obstacle. In our familiar 4 dimensions of spacetime, the theory can be made renormalizable, meaning its calculations avoid those catastrophic infinities. But when physicists attempt to extend it to higher dimensions, the framework needed to connect with string theory's extra dimensions, the infinities, return. The theory becomes non-renormalizable in dimensions above 4, suggesting that by itself it is not a complete, standalone theory of quantum gravity. It is a powerful and necessary piece of a larger puzzle. Supergravity's legacy is that of a crucial translator, a language that allows the concepts of supersymmetry and particle physics to speak directly to the geometry of gravity. It shows us that if the cosmos possesses this profound symmetry, then gravity cannot be an isolated force. It must be part of a family with a fermionic shadow that completes its nature. The vast symphony of string theory plays in countless different keys, each distinct vibration pattern of the extra dimensions, a specific way they can curl and fold upon themselves, creates what physicists call a vacuum state. This is not an empty void, but a stable configuration of the universe with its own unique set of physical laws, its own values for the constants of nature, like the strength of gravity or the mass of an electron. The number of these possible configurations is not just large, it is astronomically vast, a number so immense it dwarfs the count of atoms in our observable universe. This is the string theory landscape, a cosmic terrain of mind-boggling possibility where every valley represents a universe with a different rulebook. Our cosmos, with its specific, life-permitting constants, is just one fertile plot in this endless, sprawling wilderness. This landscape directly fuels one of the most profound and contentious ideas in modern cosmology, the multiverse. If our universe began in a period of rapid, exponential expansion called cosmic inflation, as leading models suggest, then that inflation may not have been a one-time event. It could be eternal. In this picture, the inflating spacetime is like a boiling pot of water that never stops boiling. Random quantum fluctuations can cause pockets of this inflating fabric to drop out of the rapid expansion and settle into one of the many stable vacuum states from the string theory landscape. Each of these pockets becomes a separate bubble universe, forever pinched off from our own, evolving with its own distinct physics. In some, gravity might be so strong that stars form and burn out in an instant. In others, the nuclear forces might be too weak to bind atoms, leaving only a diffuse haze of particles. Our universe is not special. It is simply one bubble that, by random chance, had the right combination of constants to allow for the formation of galaxies, stars, planets, and ultimately, life. This leads directly to the anthropic principle, a logical but controversial tool for explanation. It states that the observed constants of our universe must be compatible with the existence of observers like us, because we are here to observe them. In an infinite multiverse where every possible set of laws is realized somewhere, it is no surprise that we find ourselves in one of the rare, finely tuned bubbles capable of supporting consciousness. The multiverse idea shifts the question from why are our constants so perfectly tuned for life to in which of the countless universes would life inevitably arise. For some, this is a profound insight, a natural extension of inflation and string theory that dissolves the mystery of fine-tuning. For others, it is a philosophical retreat, an untestable hypothesis that explains everything and therefore predicts nothing. It places our cosmic home within an unimaginable, frothing sea of alien realities, leaving us to wonder if the ultimate laws of physics are not laws at all, but merely the local bylaws of our particular fortunate bubble. Our bubble in the multiverse may be the only part of reality we can ever truly know. Causal patch cosmology offers a pragmatic, almost humble, response to the dizzying infinities of eternal inflation. Instead of wrestling with the entire, unobservable multiverse, it asks a focused question. What is the complete set of events that a single observer could ever possibly see or influence? The answer is their causal patch, a finite region of spacetime bounded by the limits of light and causality. For any observer, from a person on Earth to an astronaut adrift between galaxies, the past is defined by the cone of light that has had time to reach them since the Big Bang. The future is defined by the cone of light signals they can still send before hitting a boundary, like the cosmic event horizon created by our universe's accelerated expansion. These two cones intersect to form a diamond-shaped region in spacetime, Raphael Bousso's causal diamond. This diamond contains every event that is causally connected to that observer's entire history, the sum total of their possible experience. Outside this diamond, events are forever irrelevant because no signal, no influence, no information can ever cross into it. The theory then applies the holographic principle directly to this finite, manageable region. The boundary of the causal diamond is not a passive edge, it is a holographic screen. All the information describing everything that happens within the diamond, every star that forms, every particle collision, every thought in the observer's mind, is encoded on this two-dimensional surface. Physics is no longer about the entire ungraspable cosmos. It is about the physics of this screen and the finite quantum states it can hold. This framework provides a powerful solution to the notorious measure problem of the multiverse. When you have an infinite number of bubble universes, calculating probabilities becomes meaningless. How do you determine the likelihood of our specific constants if every possible outcome occurs an infinite number of times? Causal patch cosmology cuts through this by insisting that a sensible prediction can only be made within a single, finite causal patch. You do not sample from the infinite multiverse. You ask what a typical observer within one self-contained patch would see. This refocuses cosmology on what is actually predictable and, in principle, testable. The implications for the arrow of time are profound. The causal diamond has a beginning, the Big Bang, and an end, the final moment when the observer's future light cone closes due to cosmic acceleration. Entropy is low at the diamond's beginning and grows toward its end. This creates a clear thermodynamic arrow of time that is intrinsically tied to the finite information content of the patch. The flow of time is the process of this finite system evolving from order to disorder. Finally, it offers a stark vision for the ultimate fate of information in an accelerating universe. As expansion accelerates, more and more galaxies disappear beyond our cosmic event horizon. Their light will never reach us again. In causal patch terms, the holographic screen at the boundary gradually loses degrees of freedom. Information about those distant galaxies is not destroyed, but it is permanently archived on a receding screen that we can no longer access. In the far, far future, an observer's causal patch may contain only their own galaxy, then only their star, then perhaps only a vast, cold emptiness. The universe does not end with a bang, but with a gradual fading of connections, a quiet simplification of reality into a single, frozen quantum state on the final screen. It is a theory that finds cosmic meaning not in endless expanse, but in the finite story contained within the light of one life. The smooth, local world of cause and effect may be another comforting illusion. Non-local gravity theories propose that an object can be directly influenced by another, no matter the distance, without any signal or field passing through the space in between. This is not magic, it is a fundamental feature of the geometry of reality, where two points can be connected in a way that bypasses the conventional path between them. To achieve this mathematically, physicists introduce operators with infinite derivatives into the equations of gravity. These terms act like a cosmic blurring tool, smearing out interactions over a region of spacetime instead of concentrating them at a single, sharp point. Imagine dropping a stone into a still pond. In a local theory, the ripples spread out smoothly from the point of impact. In a non-local theory with infinite derivatives, the splash would somehow affect the entire pond at once, as if the water's memory of being disturbed was woven into its entire fabric simultaneously. This profound smearing offers a breathtakingly clean resolution to the curse of singularities. In the heart of a black hole or at the Big Bang, where density and curvature would normally spike to infinity, the non-local smearing prevents the spike. The gravitational interaction is distributed, softening the blow so that what was a catastrophic, infinitely dense point becomes a finite, albeit extreme, region of high density. The singularity simply dissolves into a fuzzy quantum cloud. Many researchers suspect this non-locality is not an exotic add-on, but a generic, unavoidable prediction of any consistent theory of quantum gravity. The holographic principle strongly hints at it by suggesting that what happens in a volume is determined by information on its boundary, a deeply non-local connection. Black hole complementarity, where information is both inside the horizon and encoded on it, also points toward a reality where locality is an emergent, approximate concept that breaks down under extreme scrutiny. The central challenge for these theories is as stark as it is vital. How do you incorporate such spooky connections without completely shattering our understanding of causality? If effects can precede their causes in some frames of reference, the logical foundation of physics crumbles. The most promising models are built with exquisite care, crafting their infinite derivative structures to respect a weakened form of causality on average, ensuring that while influences can be delocalized, they cannot be used to send signals backwards in time to create paradoxes. It is a delicate dance on the edge of paradox, suggesting that the universe may be fundamentally interconnected in ways that defy our classical intuition, holding itself together not by a chain of local causes, but by a web of immediate, if subtle, relationship. Even in a region of perfect emptiness where no force tugs at a particle, gravity can still leave its ghostly signature. This is the gravitational Aharonov-Bohm effect, a subtle quantum whisper that reveals a deeper layer of reality. To understand it, we first look to its more famous sibling in electromagnetism. In the original Aharonov-Bohm effect, an electron traveling near a confined magnetic field, but never entering the region where the field itself exists, will still have its quantum wave shifted. The electron is affected not by the magnetic field, but by the electromagnetic potential, a more fundamental mathematical object that lives even in force-free zones. It is as if a ship's course is altered not by feeling the wind, but by sensing the map of pressure differences across a calm sea. The gravitational version proposes something just as strange. According to general relativity, mass and energy create not just the curvature we call gravity, but also a twisting in the fabric of spacetime called gravitomagnetism, a subtle drag caused by rotating masses. The gravitational Aharonov-Bohm effect suggests that a quantum particle, like a neutron or a cold atom, could pass through a region where the gravitational force is zero, yet still acquire a phase shift from the gravitomagnetic potential surrounding that region. Imagine sending two identical particles along separate paths around a massive, rotating cylinder. Even if both paths are meticulously arranged to feel identical classical gravity, the one that loops around the cylinder's rotation should experience a different gravitational potential, a twist in the spacetime map. When the two particle waves recombine, this difference would create an interference pattern, a striping of light and dark that betrays the hidden presence of the gravitational potential. This is not science fiction, it is the goal of incredibly precise experiments using neutron or atom interferometers. These devices split a beam of quantum particles, send the separate beams along different paths in a gravitational field, and then reunite them to see if their waves still match. Detecting this specific phase shift would be a monumental achievement, the first laboratory observation of a phenomenon that is purely quantum and purely gravitational. It would prove that gravity, like electromagnetism, has a quantum potential that matters, a field that writes its influence directly onto the quantum phase of a particle. This tiny shift in a wave pattern would be a direct probe of the mysterious interface where quantum mechanics meets the geometry of general relativity, a fingerprint left by the hidden hand of quantum gravity itself. The relentless tick of a clock may be a symptom of cosmic disorder. Our 28th theory, the thermal time hypothesis, proposes that time itself is not a fundamental feature of the universe. It is an emergent phenomenon, a story told by thermodynamics. Physicists Elaine Conz and Carlo Rovelli offered a radical new definition. Time, they argue, is what we perceive when a system is not in perfect equilibrium. It is the flow generated by the difference between a system's current state and its final, uniform state of maximum entropy. In their framework, any arbitrary quantum state of the universe defines a mathematical flow, a one-parameter family of transformations. This flow is what we experience as the passage of time. It is not that time makes things change, but that change, or more precisely the statistical tendency toward disorder, creates the illusion of a time parameter. To grasp this, picture a cup of hot coffee sitting in a cool room. The coffee has a temperature, a statistical property describing the energy of its molecules. That temperature defines a natural rhythm, a thermal time. As the coffee cools toward room temperature, approaching equilibrium with its environment, we witness events: steam rising, currents swirling. The thermal time flow is active. Now imagine the coffee and the room finally reaching the exact same temperature. The system is in perfect thermal equilibrium. No more heat flows, no currents stir, no events distinguish one moment from the next. In this state of ultimate balance, the thermal time flow would vanish. There would be no internal clock, no change to measure, and thus no meaningful experience of time. This hypothesis weaves a profound link between the three great pillars of our story: gravity, quantum theory, and thermodynamics. It suggests that the arrow of time, the reason we remember the past and not the future, is intrinsically tied to the universe's journey from a low-entropy Big Bang toward a high-entropy future. In the context of quantum gravity, where time often vanishes from the fundamental equations, the thermal time hypothesis provides a way to recover it. The flow of time emerges from the specific, out-of-equilibrium quantum state our universe happens to be in. It offers a chilling yet beautiful vision of the ultimate fate of the cosmos. If the universe reaches a true state of heat death, a perfect equilibrium where energy is uniformly smeared into a thin, cold haze, then time itself would cease to have any operational meaning. The cosmos would not end in a moment, but in a timeless, eventless forever. The clock does not stop ticking because it runs down, but because the very concept of a tick loses all definition. The universe may be the ultimate quantum computer, and space-time its most elegant software. This 29th theory ventures into the most abstract and promising frontier of all, where gravity is built not from geometry but from information. It is called the from-qubit paradigm, a radical idea suggesting that the classical world of objects, distances, and space-time emerges from the qubit, the fundamental unit of quantum information. Here, the tools are not borrowed from differential geometry, but from quantum computing and information theory. The central ingredients are entanglement, complexity, and error correction. In this view, the fabric of reality is a vast, dynamic network of quantum entanglement. Each connection between particles is a thread, and the collective weave of countless threads stitches together the very notion of proximity and geometry. The more entangled two regions are, the more strongly they are connected, and this connection can manifest as a physical bridge in space-time. This is not just philosophy, it has a precise mathematical heart. The Ryu-Takenogi formula provides a breathtakingly direct link. It states that the entanglement entropy between a region of space and its surroundings is proportional to the area of the minimal surface that separates them. In simpler terms, the amount of quantum information shared across a boundary is measured by a geometric area. This is a holographic revelation showing that entanglement, a purely quantum property, directly builds the geometry of space itself. It is as if the connectedness of information literally carves out the distances we measure. But how does this fragile quantum information produce the stable, classical world we navigate? The answer may lie in quantum error correction. In a quantum computer, information is incredibly delicate, easily corrupted by noise from the environment. To protect it, scientists use error-correcting codes, which spread a single logical piece of information across many physical qubits in a redundant, entangled web. This makes the information resilient. Local disturbances cannot destroy it because it is not stored in any one place. Remarkably, the geometry of space-time appears to behave exactly like such a code. Our experience of locality, the fact that things here are influenced primarily by things nearby, might be an emergent property of this cosmic error correction. A particle's position is not a single datum at a point, it is information smeared across a vast, entangled network. To damage that information, you would have to disrupt a significant fraction of the network, which is incredibly hard. This is why space-time is robust, why it seems continuous and classical despite being built from jittery quantum bits. The picture that emerges is stunning. The universe is not a container running computations, it is the computation. Space-time and gravity are the operating system that emerges from the ceaseless, entangled processing of quantum information. A black hole is not just an object, it is a region of maximal entanglement entropy. Its event horizon a firewall of information density. The expansion of the universe could be the gradual increase in quantum complexity, the system running more and more intricate operations. We are living inside a cosmic quantum processor, and the laws of physics are its source code, written in the language of entanglement and error correction. The final theory is not a vision of the cosmos, but a map for the journey back to our own world. After soaring through landscapes of loops, strings, and holograms, we must plant our feet back on solid ground, asking the most crucial question of all: how will we ever know which idea is true? The quest for quantum gravity now lives not just on chalkboards, but at the bleeding edge of experimental physics, where scientists hunt for its subtle fingerprints in the data. These are the experimental and observational probes, the real-world tests that could one day turn speculation into discovery. The challenge is immense. The Planck energy, where quantum gravity effect should scream, is a quadrillion times beyond the reach of our mightiest particle colliders. Yet, if the theories are right, whispers of that hidden realm may have already echoed across the universe, leaving faint traces we are now clever enough to find. One whisper might come from the violent death of massive stars. When a star collapses into a gamma-ray burst, it unleashes a torrent of photons across a staggering range of energies. According to some models of granular spacetime, like those in loop quantum gravity, higher energy photons could interact very slightly differently with the quantum foam of space, causing a minute delay compared to their lower energy siblings. It would be a delay of mere milliseconds over billions of light years, but by comparing the arrival times of these photons, observatories like the Fermi Gamma Ray Space Telescope are listening for this telltale lag, a potential sign that light's universal speed limit has quantum cracks. Another echo from the dawn of time is etched into the oldest light in the universe. The cosmic microwave background, that faint afterglow of the Big Bang, is not perfectly uniform. Its polarization, the specific direction its light waves wiggle, carries patterns that could be the fossilized imprint of gravitational waves from the universe's first frantic moments. Specific signatures in this polarization, known as B-modes, could reveal whether those primordial waves were amplified by a period of cosmic inflation driven by a quantum gravity field. Telescopes at the South Pole and in the high Chilean deserts are staring at this cold light, searching for a curl in its pattern that could be a direct message from the quantum birth of spacetime. The newest messengers, gravitational waves, open another frontier. When future observatories like the Laser Interferometer Space Antenna, LISA, detect the ripples from colliding supermassive black holes, they will probe gravity with unimaginable precision. Some theories predict that the fabric of spacetime might have a subtle graininess or dispersion, causing different frequencies of gravitational waves to travel at very slightly different speeds. Finding such an effect would be like hearing a cosmic chord where the high notes arrive out of sync with the low notes, a direct signature of a discrete quantum spacetime. On Earth, the hunt continues in tunnels deep underground and in pristine laboratories. While we cannot reach Planck-scale collisions, some models suggest that ultra-high-energy cosmic rays, particles from deep space striking our atmosphere with energies far beyond any collider, could produce exotic, fleeting effects predicted by theories like string theory or extra dimensions. Meanwhile, exquisitely sensitive tests of the equivalence principle, the idea that all objects fall at the same rate in a vacuum, are ongoing. Any detectable violation would shake the foundations of general relativity and point directly toward a new gravitational paradigm. The message is clear: the energy barrier is not a wall but a puzzle. By combining the cosmic laboratory of the early universe with the precision of quantum sensors and the patience of astronomers, we are building a net fine enough to catch the ghost of quantum gravity. The answer may not come as a thunderclap, but as a tiny anomaly in a data stream, a whisper in the static that says, the universe is woven from something stranger than we dream. From loops of space to vibrating strings, from holographic projections to emergent illusions, the landscape of quantum gravity is a testament to human imagination at its most daring. We have journeyed through 30 distinct visions, each a universe in itself, built on the conviction that our reality must make sense. Amidst this breathtaking diversity, powerful common threads emerge, pointing toward the shape of a final answer. The smooth continuum of space and time seems destined to be replaced by something discrete, whether pixels, networks, or blocks. The holographic principle, born from black hole paradoxes, now weaves through countless theories, suggesting our three-dimensional world is a projection from a deeper, two-dimensional reality. And time itself, that most persistent flow, appears again and again as an emergent property, a story told by thermodynamics or a rhythm born from quantum entanglement. These are not random guesses, they are the echoes of a deeper logic, the clues left behind by a universe that refuses to be both quantum and geometric in the ways we once understood. This is not a sign of failure, but of a field vibrantly alive, probing the absolute limits of knowledge. The quest to unite quantum mechanics and general relativity remains the single greatest puzzle in all of science, a mystery that touches the nature of reality itself. It asks what space and time are made of, and in doing so, asks what we are made of. So stay curious, the answer is out there, waiting in the data of a gamma-ray burst, in the subtle twist of a lab experiment, or in the next revolutionary thought. If you want to explore more of these space mysteries, subscribe for our deep dives into black holes, dark matter, and the edges of the cosmos. And let us know in the comments below which of these 30 theories about the universe feels the most compelling to you.